Okay, hello everyone. My name is Hannah, and today I will be presenting our work building out editing environments to enable higher level control of knit surface patterning effects. So when thinking about designing knit things, I want to draw a distinction between the overall topology of a three-dimensional garment and the surface level patterning effects, some examples of which you can see here. So there are many different kinds of color and texture effects we can use when designing knit things. But sometimes when designing these fabric level effects, we have to work at a level of abstraction which captures elements of the knitting process or how the fabric is formed. But as you might be able to tell, the process or the relationship between this notation and the outcome can often be pretty unintuitive. And so how do we address this? How can a design tool help us navigate this notational physical divide? At Kai in May, I presented Knitscape, which is a design and simulation environment for slip and tuck colorwork patterns. And this specifically explores a knitting technique where there's this very unintuitive correspondence between an input pattern and the resulting fabric. So the goal of Knitscape was to make it easier to design these patterns by coupling a charting environment with a yarn visualization and physics simulation. As you change the pattern representation on the left, we regenerate the yarn topology from the instruction chart. And this enables you to very quickly develop an understanding of how knitting operations work together with colors, with changes in yarn color to produce this overall effect. So here you can see this vertical column of slipped stitches stretches up one long loop of blue, and then when we run the physics simulation, that loop contracts to pull on the surrounding fabric, which turns those rectangles into hexagons. So this editing environment with a synchronized chart and yarn visualization is really nice for rapidly exploring this emergent material effect of this colorwork technique. And here's a collection of swatches we made with the simulations on the left and the real swatches on the right. But most garments aren't just made from one individual pattern. They use combinations of level behavior and different stitch structures to produce an overall effect. So if we take a close look at this sweater, there's a lot going on. There's a lot of different texture patterns like cables, braids, and lattice structures, which make it look like there are actual ropes being twisted around each other. So the goal of the work I'm presenting today was to enable higher level manipulation of these low level material effects through composable design primitives. So we've extended the original version of Knitscape. In this new editor, you can make blocks of knitting instructions, which are called stitch blocks, and blocks of yarn assignments, which are called yarn blocks. And then these blocks, it's a bit of a delay. And these blocks can be associated with vector paths and closed boundaries, which can be drawn on top of the raster chart of instructions. I don't know why my slides are not advancing. Okay. Oh my gosh. Sorry, I have no control over this progression of my slides right now. Just trying to get to the next one. But together, these combined yarn blocks and stitch blocks create 4 types of composable primitives. Stitch paths, yarn paths, stitch fills, and yarn fills. And I'll go through each of those right now. Once my slides move there. Very embarrassing. So for stitch paths, you can edit the stitch block associated with the path, resize it, reposition it relative to the path, and then, of course, modify the vector path itself, which you can see me doing here in this GIF. Okay. And then you can create much more complex behavior even with very simple stitch blocks, like this braid pattern. And of course, we are regenerating the topology of the yarns visualized on the right whenever changes are made to the vectors or the associated stitch or yarn blocks in the charting environment on the left. Stitch fills are produced by associating the stitch block with a closed path or boundary, and these are rasterized using a polygon scanline approach. So here I'm editing different kinds of rib structures in this trapezoid. And here's an example of using a stitch fill to make a lace pattern, and this one is taken from a book on Japanese lace. Yarn paths work more or less the same way as stitch paths. You can assign yarns to blocks and then move them on a vector path. And for yarn paths and fills, we are planning the yarn separation when generating the visualization. So you can see when I flip over the fabric to view the back, the blue yarn leaves these long floats when it has to travel over the yellow yarn. And then the same thing for yarn fills. We are again rasterizing using the scanline approach and regenerating the yarn topology whenever changes are made in the editing environment. And here it's much more apparent when I flip over the fabric that there are these long floats across the back of this patch of yellow yarn, except when the yellow yarn boundary is all the way at the edge of the piece. And this will be relevant later. With yarn blocks, we can also create these repeating patterns which fill vector boundaries, and this can be used to make things like the doodle cow that you see here. So now I want to talk about how we've incorporated these composable elements into an actual design tool. So this is the supported operation set, which we have extended from the original version of Knitscape. It includes front and back bed knits, or knits and purls, miss, which means that a yarn will pass by a needle without being placed onto the needle or pulled through a loop, tuck, which means that the yarn loop will be added to the needle without being pulled through the loop, and then finally we have a variety of compound transfer commands, which basically mean knit a stitch and then move it to a new position. This particular charting language is limited to a single-faced or single-layer fabric, but it could be feasibly extended to a more complete charting language in the future. So in order to more easily visualize the stitch and yarn information in the same environment, we have two different color display modes for the charting environment, which you can toggle depending on what you're doing. One uses the yarn color assignment of that cell, and the other uses whatever color is assigned to a particular stitch. And the symbol of the stitch is assigned to the cell is always visible. In the charting environment, you can modify the layers of the vector elements. So here you can see me moving these different stitch and yarn fills between different layers. And then we also have a transparent stitch or yarn command, which just inherits the value of this cell below it. And you can use that to create these different layered effects. So to enable the design of shaped panels, which is very important for designing actual garments, we have added these optional boundary shaping commands, which automatically place shaping instructions at the vector boundary. And this is nice because with the instructions attached to the actual vector boundary, it's very easy to modify the overall garment shape without performing destructive edits to an underlying raster chart. And then we also have an optional join condition for a yarn boundary, which will add tuck stitches when two yarns meet at a boundary, which cinches together the yarn. And this is really important when you're designing intarsia patterns like you see here. So whenever there is not a boundary join and we run the relaxation, you can see how there is this gap forming in between the yellow and blue yarns. And once we enable the yarn join, there is no longer a gap. As edits are being made, we're constantly regenerating the program for the knitting machine, which you can see as you edit the pattern. And this program was generated specifically for the knitterate, but could feasibly be extended to additional machines in the future. So now I want to talk about some of the cool things we can design with this way of editing knitting charts and fun applications. So we can, of course, layer the vector elements to start building up more complex designs. So this is a sleeve with a ribbed cuff. And as I drag the side over, you can see that it's automatically generating those shaping commands. We can design more complex intarsia patterns. So here is a pattern that is a bit similar to the one that I just showed, but now we're using an additional yarn boundary to remove, to make that square of blue float in the center of the swatch by having this other yarn knit the stitches on one side of it. And again, joining the yarn at the boundary using this yarn join technique. And then using the same technique, we can start to design more complex intarsia patterns, which you can see me doing here. And this is a pattern for an intarsia-based sensing structure. So here, when we knit the orange areas with conductive yarn, we can create a capacitive sensing touchpad and use that for volume control. And then we can also use the yarn paths to explore this higher level material behavior. Here you're using yarn paths to design an interdigitated electrode structure which can sense bend and pressure on this mitten and swatch. And since submitting the paper, I've been working on this elastic rod-based 3D simulation, which quite literally captures another dimension of the fabric structure. This is still in development, but is not part of any research contribution. And I wanted to show that it enables us to now explore this three-dimensional deformation of things like origami pleat patterns. So here we've created stitch paths that represent mountain and valley folds, and when they are overlaid onto this garter stitch background, it makes a pleat pattern which we can simulate. And it looks pretty good. So I see a lot of avenues for where this work could go next. There are some obvious quality of life improvements to the tool. We could always incorporate more forms of visual feedback, like highlighting floats over some maximum distance. Can continue to extend the topology model to support multi-layer fabrics and circular knitting, and as well as more import and export formats. I'm particularly interested in building an iteration for hand knitting chart notation because I think that would open up this tool to a much broader audience. But beyond that, I think there's a lot of really interesting work that could happen with more advanced editing tools. There's been a lot of prior work at UIST that is focused on things like bidirectional editing and parametric design of vector graphics. And I think bringing that work to the domain of knit programming could be really interesting. And then also making it possible to do things like program block conditions could be really powerful. So instead of having those hard-coded boundary conditions I showed earlier, we could have someone could be able to define custom blocks based on path angle or the value of cells at a lower layer. So that is all I have for you today, and I will take questions.
Hi, Hannah. I'm Jack Foreman. I'm a PhD at MIT Media Lab. Thank you so much for the wonderful talk. I've used and loved Netscape before in the past, and I was really excited to see this work. And when thinking about maybe the future direction, one thing that inspired me when you said was about being able to remove the abstraction to make it a much more natural process. And I think that that could maybe then be extended to also the functional and perceptive qualities of fabrics, like we design maybe certain knit structures because they're warmer, or certain knit structures because they can have embedded sensing, which I think is very relevant also to some of these 3D things. Have you also thought about being able to also be able to develop this abstraction so that you can say that you want to add a breathable section here or a stretchable section here, or embedded wiring?
Yeah, absolutely. I mean, right now, what we've built so far enable you to really iterate very quickly on those different structures, and test them, and hopefully just copy and paste the blocks into different areas, and then maybe label something as breathable or more stretchy, or whatever you'd be interested in. But one thing that I am really interested in is working on that bidirectional design. So, how could we actually work directly in the visualization environment and manipulate the yarns directly to change the structure for whatever, application we're building for. And I think that that could be very useful for some of the things that you're working on, and I'd love to talk more about it.
I'm sure we will. Thank you so much.
Hi, Alexandra. I'm from Carnegie Mellon University. This is really cool work. I was wondering if you, simulate the material properties too. So if you, I don't know, have slightly stretchier yarns or stiffer yarns, and then also if you could, have multi-yarn knitting or so in the simulation. Is that possible?
Yeah, they're definitely. Maybe I didn't have any images of it, but I definitely have simulations with multiple yarns. Right now, the actual simulation is hard-coded, but it would be very feasible, realistic to extend it to lower-level control of the material properties of individual yarns. Right now, it's just a spring constant, but there are other things that we could change and extend the simulation further. Yeah.
Cool. Thank you.